Hello class and welcome to week 3. This week we're going to be talking about controls, various types of controls, both hardware as well as access controls. We're going to look at trust and trust boundaries as they apply to internal devices, internal systems, as well as connectivity to external networks. And we're also going to take a look at remote access and how remote access security is changing and new ways to secure the bring your own devices that employees are demanding that they be able to use, as well as management. And we're also going to take a look at aggregate risk. After you've applied all of your controls, there's always some risk left, and that's called aggregate risk. And we'll take a look at what makes up aggregate risk. So let's jump right in. So the control categories, there's 3: administrative, physical, technical, logical. Technical, logical, some people call them technical controls, some logical controls, but they're essentially the same thing. Physical controls are made up by walls, doors, and fences, and that type of thing. And they're designed to deter an intruder. And if an intruder is not deterred, then the controls should delay the intruder until he or she can be detected and detained. So that's the purpose of physical controls. We're not going to spend a lot of time on that in this lecture. However, it's important to always take physical controls into consideration when you're doing a risk assessment for a system or your data center. Because if an intruder gains physical access to your systems, then no amount of controls are going to work to prevent that intruder from getting to your data. Administrative controls consists of policies, which are general statements of intent by management as to what outcomes they want from their security program. And policies, as you might remember from CMGT 430 or 400, are applied at 3 different levels. They're applied at system, at issue, and at enterprise. To support policies, we develop standards and guidelines. Standards are things that our IT staff or our business users must do to remain compliant. And guidelines are recommendations, although sometimes strong recommendations, about how we should be compliant with policy. However, the guidelines allow some leeway. They allow some room for creativity, which is always good. Whenever you can apply a guideline instead of a standard, it allows some room for getting creative, for applying good security at low cost. Processes support the standards and guidelines. For everything that a business user or a technical user does, there should be a process. A process ensures that users perform the same set of tasks in the same way every time, and resulting in consistent outcomes. Those outcomes then are measured to determine whether or not they're compliant with policy. If they're not, then we go back and look at the processes. The thing to remember is we don't manage the processes, we manage the outcomes. Another administrative control is root cause analysis. When there's an incident or something doesn't go the way it should have gone, we sit down as a group without pointing fingers and we work through the issue. What happened, what was supposed to happen, and how can we prevent this thing that we didn't want to happen? How can we prevent that from happening again? What root cause analysis does is it prevents us from fixing symptoms and allows us to identify what is actually causing the problem, fix that so that it doesn't happen again. Another administrative control is response, which includes your business continuity planning, What happens if a server goes down? Disaster recovery for those catastrophic events that may occur. And they also includes what to do if an intrusion is detected. It includes an incident response plan that's supported by a trained response team. The faster that you can respond, the less business impact there is when something happens. And audits are our last administrative control on this slide. They are used to look at outcomes and determine whether they're in line with policies. Remember, we talked about processes are supposed to give us consistent outcomes. Then those outcomes are compared to policy. The audits compare those process outcomes to policy. And again, if there's a problem, the auditors don't fix the process. They simply report to management that there's a problem with the outcomes, and it's management's responsibility then, let's say if it's an IT policy, it would be IT management's responsibility then to go in, take a look at the policy or the process, and adjust the process so that the outcomes are more in line with policy. Now, having said that, sometimes the policies need adjustment. Now, that doesn't mean that every time that there's an audit finding that we don't like, that we go just change the policy to bring it in line with what we're actually doing. However, sometimes the outcomes that are expected by policy are no longer reasonable and appropriate for our business. When that happens, we need to go back and adjust the policy. One way to prevent these things from coming up in audits is to do annual reviews of policies to ensure that the policies remain in step with the business, and then adjust our processes accordingly. Again, policies state management's general intent for security outcomes. They're supported by standards, guidelines, processes, and audits. So let's take a deeper look at business continuity planning. The purpose of business continuity planning is quick response to an event, a business continuity event, and restoring a system or systems to operational state as quickly as possible. Especially making sure that the downtime does not exceed maximum tolerable downtime. Maximum tolerable downtime is the amount of time a system can be down before the business suffers irreparable harm. A business continuity event is any condition or set of conditions that interrupts one or more business processes. So a business continuity event can be anything from a switch port failing to the entire switch going down. Or business continuity events also can be a tornado moving through town and wiping out your data center. Disaster recovery events are included in or under the umbrella of business continuity events. Disaster recovery restores business processes following a catastrophic event. So, how do we plan for this? Well, we plan for worst case scenarios. If we can bring the processes back up when we've lost the entire data center, that means that we understand every system that's within the data center, what processes and other systems that each system interfaces with, and that also means that we've backed up those systems in a way and documented them in a way that we can bring them up at any time. If we have that information, then we can resort to that information when a server goes down, or when a cable fails, or when a database for some reason is corrupted. If we plan for worst case scenarios, we don't have to plan for every single event that happens, because we already have everything we need to adjust to the event that has occurred and recover from it. Another part of business continuity planning is making sure we have the right backups. There are three types of backups that we're going to talk about. There's full, where we back up everything. Incremental, where we back up everything that changed since the last backup of any kind. And a differential that backs up everything that changed since the last full backup. So an incremental backup will back up everything that changed since the last full or incremental or differential. It doesn't matter. If it's changed since the last backup, it's going to get backed up. A differential only backs up what's changed since the last full. So you could do a full, 3 incrementals, and then a differential, and the differential is still going to back up everything that the incrementals backed up. The reason that we have these different kinds of backups is because we're often limited in our backup windows. Usually, we only have one night a week that we're able to do a full backup. It takes a long time in a large company to do a full backup. Sometimes it can take 12, 14 hours, depending on the media, depending on how much storage you have, etc. It also takes a long time to restore a full backup. So, if we have incremental backups, we can cut our backup times significantly by only backing up what's changed since the last incremental backup. The problem with incremental backups is that I have to restore every single incremental backup since the last full backup. So if I do a full backup on Sunday and I do incrementals the rest of the days of the week, and on Friday my system fails and I need to restore from backup, I have to restore the Sunday backup and Sunday full backup, and then I have to restore the incrementals from Monday, Tuesday, Wednesday, Thursday. A differential gives us a balance between full and incremental. If we have the same scenario, that we have a failure on a Friday, when our full backups are on Sundays and differentials through the rest of the week, I only have to restore my full backup and then Thursday's differential. Remember that the differential backups back up everything since the last full. So that in most cases will result in a faster restoration time. It takes longer as the week goes on to back up, but not as long as a full. And I can restore much faster. Which backups approaches you use depends on your business, depends on what your operating hours are like, depends on what kind of backup windows you have. But these are the tools that you use to make sure you back up every day in the right way so that you can restore within the maximum tolerable downtimes for your systems. Your backups should also be stored off-site. At least one of your backups should be off-site. Your full plus your most recent incremental or differential. Off-site means outside of a 25-mile perimeter. That's just a general rule of thumb. The 25 miles is considered reasonable because any kind of event, natural event, that would affect your main office probably isn't going to extend out for 25 miles. Your the power grids and those kinds of things probably, so that you can have access to secure areas, probably aren't going to be affected by something that happens at your corporate office. The same thing won't affect where your tapes are located. That's also the same rule for a co-location or a hot site. Make sure that your off-site storage is climate controlled, and that it has reasonable and appropriate security to ensure that only you can get to your tapes and someone else can't walk off with them, or your tapes or your disks, however you're storing your backups. Today, many organizations are storing their backups in the cloud. They're backing up to the cloud. Also, they have disk that they have at Colo, where they can back up across a connection between their primary data center and a secondary data center, and just back up their data over there, and if something happens, they can just copy it back or copy it to a hot site. So the media types of tape and disk are starting to give way to cloud and co-location. And we're not going to go into those things in a lot of detail, but it's important to know about the different approaches and apply the right one to your business. So now let's take a look at technical controls. Technical controls fall into two major categories for the purposes of this class: prevent and detect. And then we're going to include encryption, although it's a type of access control which falls under prevention. We're going to look at it as a separate control. Prevention controls try to keep bad things from happening. We can't always prevent bad things from happening. So we also need detection controls. Detection controls detect when something bad is happening and alerts us to it and allows us to respond appropriately. Notice in this slide that IPS is both a prevention and a detection control, because it can detect or it can block depending on the business rules you've put into the device. Log management is under detection is the ability to collect logs from all over the network, aggregate them, and assess them, and using that information along with the analysis of net flow, which is the analysis of packets as they flow through devices within our network, or which can be through switches from one server to another server. And you put all that information together and it looks for anomalous behavior in the network or on a system. And that's behavior that is outside the norm for your unique network activity. And encryption, of course, garbles any kind of data so that it cannot be read except by someone who has the key. Many times the key is protected by a password. If you have the password and you have the right user ID, you can unencrypt the file. So it's a type of access control. So let's look at firewalls a little deeper. So a firewall, remember, is a prevention control. Best practice dictates that we configure our firewalls as soon as we get them to block everything, all traffic, both in and out of our network, and then or a network segment, and then open only the port IP address pairs that are necessary to conduct business. And it doesn't mean just blocking things coming in. It also means making sure that a server in your data center can only connect to devices on the outside that you know about and have approved. So all other connections for your server should be blocked. What this does is it helps to prevent an infected server from connecting to a malicious server and copying all your data there. You want to make sure that your firewall operating systems are kept up to date. Again, patching. You want to use your firewalls internally for your security zones on your network, as well as at the perimeter. And there are two types of firewalls. There are network and host firewalls. A network firewall is just what it sounds like. It gets connected onto your network, and all the traffic that has to pass through it before it gets from one side of the firewall to the other. So for example, if I'm coming into your data center from the internet, I'm going to have to hit that firewall. The firewall is going to look at my traffic and say, okay, I'm going to allow this, and then my traffic will come out the other side and be routed to the appropriate place. If my firewall looks at it and the traffic from my device is not allowed or not explicitly allowed, then it's going to drop my traffic and I'm never going to get to the other side of the firewall. A host firewall is what runs on our desktops, our mobile devices, etc. it performs the same tasks. It blocks applications on our system from doing things that are unexpected, and it keeps external applications from doing things unexpected to our device. IPS and IDS. First of all, there's no such thing as an IPDS. I know that the reading in these classes has brought up IPDS, but that's just something that the author came up with. An IPS can do both. An IPS can do both prevention and detection. Depends on how you set it up. An IDS can only do detection. An IPS, an intrusion prevention system, detects anomalous packets and network behavior. And then it can either alert or block traffic based on the rules that you've defined within the IPS. In many cases, if you've got a log management system set up, it also is going to provide logs to the log management system so that they'll be aggregated along with the logs from your firewalls, switches, servers, etc. An IPS is placed in line with traffic. That means that traffic must pass through the IPS before it can get to its target. This is different than an IDS. An IDS is placed out of band. What that means is that an IDS is set up so that packets passing through a switch are all mirrored to the IDS or to the port where the IDS is connected. The reason we do this is because IDSs are typically inexpensive and they're not really capable of handling a lot of packets without significantly slowing down performance. So if we just simply mirror or copy the packets that are going through the switch, for example, to the port where the IDS is connected, the IDS can still look at the traffic and try to detect bad stuff without slowing down the network performance. Now, having said that, the IPS will also slow down performance. They're not necessarily as much as the IDS. Their IPS devices are designed not to do that. However, you still have to tune your IPS. You have to make sure that you don't have too many packets going through the IPS. Otherwise, you will lock it up. You will create your own denial of service condition. So when you first put in an IPS, you're going to put it in an audit mode. You're going to watch it, and you're going to tell it to ignore things on your network that are supposed to be happening. You're also going to make sure that you haven't undersized your IPS for the number of packets you expect to go through it. Once you have everything set up, and that can take 2-3 months, then you turn on the IPS and continue to tune it until you have it the way you want it, which can take probably another 2 to 3 months. So putting an IPS is not just a matter of throwing a box in your data center and plugging it in. It requires some work. So this is an example of how you might place IPS and IDS. The NIPS in the DMZ is a network level IPS as opposed to a host level IPS. A host level IPS would be on a workstation or a server, for example. In this particular example, traffic coming in through the perimeter passes through a firewall and hits the IPS. It's going to hit the IPS before it even goes to a web server or anything else. We're also not going to allow any traffic that's coming from the outside to get to the inside of our network if it can't pass the rules that are in that IPS in the DMZ. Then the traffic will pass through a second firewall. Those two firewalls together create a DMZ or an externally facing security zone, and then hits an internal network router. That router, or could also be a layer 3 enterprise switch. If you notice, the network is divided into two segments, segment A and segment B. Segment A has public and confidential data on it. Segment B has restricted data on it, which means that the data in segment B is very sensitive, and its loss or damage can cause significant damage to the business. So we add another IPS as a gateway device going into that segment. If we don't have the money to do it, to put an IPS there, we can also put an IDS there, which will provide much of the same value. It'll provide logging of what's going in and out of that segment. It'll alert on things that are not that are happening that should not be happening, and it can provide log management data. Now, we talked a lot about log management in this lecture. This is a very simple diagram of a log management environment. It's also known as an SIEM, which is a Security Incident and Event Management System. So down at the bottom of the slide, we have different systems or different devices. Each of these devices provides log information to a syslog server. Syslog is an actual format, a standard format for logs. And most SIEMs or log management systems use syslog format for collecting data and then for processing it. So the syslog server aggregates the data from logs across the network. What devices you pull logs from depends on what network segments the device is serving or protecting. Then those logs are sent near real time up to a correlation engine. The correlation engine takes the data in the logs and looks for patterns, for either known patterns of attack and we're not talking about signatures here, we're talking about behavior analysis. And it's also going to look for anything that looks really off based on what the correlation engine knows about your network. When you tune a SIEM, and you have to tune it when you put it in, you're going to tell it initially to ignore certain things. For example, if there's an event that occurs that by default the correlation engine thinks you should know about, but you know that it's supposed to happen all the time because of the way that your network is configured, you tell it to ignore that event. So that over time, the only thing the correlation engine is going to tell you about are the things that are out of the ordinary. And it's going to do that through a portal. It can also do alerts through email and text messaging and that type of thing. But the way that I did this in my last organization is I had my on-call analyst always had the portal up for the SIEM on one of his monitors. So a portal will give you the overall health of your network, and it can also, depending on the solution, tell you what the current threat environment is for organizations in your industry for that day. What a SIEM does is it gives you a good picture, overall analysis of everything that's going on across network segments of interest on your network and lets you know whether there's something you should be taking a look at. Next, we're going to take a look at access control. There are 4 types of access control that I want to talk about in this lecture: mandatory, discretionary, role-based, and policy-based. Mandatory access control is a very detailed and hard to implement approach to keeping people out of places they're not supposed to go. It's done by tagging and labeling, and we're going to see in the next slide how that works. Discretionary access control is what you get with Active Directory out of the or Windows out of the box. Users set and manage security on the items that they create. Even if an administrator does the administration, they do it by user. And even if you set up a group, in many cases, groups are not set up by administrators in a way that supports anything other than DAC. The problem with DAC is it's hard to manage. It's hard to determine who has access to what by either looking at and it's hard to determine what access an individual user has. What we want to do is control what people have access to based on their job in the organization. We want to enforce least privilege, separation of duties, and need to know based on job role. The best way to do that is to use role-based access control. Role-based access control is, in many cases, implemented via a special application that sits on top of something like Active Directory, and it uses business-defined roles to determine what a new employee should have access to. So if I have a new hire, the new hire information will be supplied to the RBAC system via a feed, and that's usually from the HR system to the RBAC solution. And then the RBAC solution goes out and creates accounts and sets the appropriate access for all the applications and other resources that the user should have access to based on his or her role in the organization. We're going to take a closer look at these of mandatory, role-based, and policy-based in a couple minutes. But in most cases, in the past, the only thing that students have had to worry about are mandatory, discretionary, and role-based access control. For many years, those have been the basic approaches to authorizing users and other devices to accessing network resources. The problem is that today, as more and more mobile devices, handheld devices, consumer devices are brought into the workplace or used on the road, role-based access control or mandatory access control are not sufficient anymore to control access based on multiple use contexts. That's where policy-based access control comes in. And again, we're going to look at that in a couple slides. So let's move on. So here's a very simple example of mandatory access control. What happens is user A and user B each have a security classification. User A has a secret classification. User B has a top secret classification. I'm using governmental classifications here because for the most part, mandatory access control is only feasible if you're protecting national defense secrets. It is too involved and costs too much to maintain for most business data. So each one of those user accounts is tagged as secret or top secret. Then the data in the databases are also tagged with confidential, secret, and top secret. What has to happen is that the classification level of the user must be the same or greater as the data classification of the data, or the user can't get to it. This sort of sits on top of role-based access control, because even though the user may be able to access the data based on classification, the user also must have a need to know to be able to access that data. So in our example here, the data is top secret. User A only has a secret clearance. So even if somebody made a mistake and put top secret data into an area where user A's role allowed her to have access to it, the mandatory access control system will block the access because there's a mismatch between the user's classification and the data's classification. User B, on the other hand, has a top secret classification and can access the data if the role that she's been configured with is supposed to have that access to that data for business operation. Role-based access control is also a little difficult to set up. And again, this basic foundation we're going to look at is also present in mandatory access control. Mandatory access control adds on top of this tagging. And as an aside, the new Windows Server environments that came out with Windows 8 provide a lot of data tagging, of role-based access control, and policy-based access controls, either built into Active Directory or as part of additional products from Microsoft or third parties that you implement on top of Active Directory. So with RBAC, you go to your data owner, and remember, a data owner is a member of senior management, usually a vice president, department head, who is responsible for a specific set of data. So, for example, the vice president of human resources would be responsible for all human resources or employee data. Reporting to the data owner would be role managers. Now, usually a role manager is just a manager or director within the department who also is very familiar with the various roles within the department and can help IT put together for each role what access is necessary. Once the role managers do that, they submit that to the data owner for approval, and the data owner looks at it for enforcement of least privilege, need to know, and separation of duties, and if everything's fine, it's approved. Once it's approved, the roles then are implemented, usually by security, in the provisioning system. So once it's in the provisioning system, you can take data from an authoritative source, and remember I discussed earlier that for new users, that's usually going to be your human resources system. So let's say a new user comes in. They're put into the human resources system, which in our graphic is the authoritative source. That information, probably during the night, is sent to the provisioning application. The provisioning application goes out and looks at roles that have been defined and compares it to, usually it's the job code for the employee that came from the HR system. Based on that job code, the provisioning system will go out to the appropriate applications or directory services, and directory services here is Active Directory, and configure accounts based on access. In the financial application, you might also have security set up that further refines that authorization. Policy-based access control is after outcomes that will protect data no matter where it's accessed from or how it's accessed. In today's businesses, we're looking for anytime, anywhere access to information. We're looking at support for bring your own device. So if somebody goes out and buys an iPad, somebody goes out and buys a smartphone, they want to be able to access data and applications in the data center, at least the email system. Managers are pushing for this very hard. In one sense, it's a very good thing because users are using devices with which they're very familiar. Usually it's a a personal device that they use for also personal business. On the other hand, it's very dangerous for an organization to not understand what kind of device is going after the data and setting restrictions based on that. So policy-based access control imposes restrictions based on the employee's role, the kind of device that the employee is trying to access the resources with, who owns the device, whether it's the company or the employee, the location from where the employee is trying to establish the connection, whether that's in the internal network or from outside the organization, what process and what data the user is trying to access with that device, whether there's single factor or multi-factor authentication in place for that type of access, and whether or not the organization wants mobile devices or any kind of device over which they have no control accessing data anytime. So for example, here we have time constraints that the VP of Finance is only allowed into finance from 6 a.m. through 8 p.m. Eastern Standard Time. Any other time it'll be blocked. So if you look down through this table, you can see that these policies that are set up in a special special solution that comes from organizations like now from Microsoft and also from Cisco and from others. If the VP of Finance tries to get into the financial application using a laptop, it's going to use multi-factor authentication, and that VP is going to be allowed in as long as it's not outside the time frame of 6 a.m. to 8 p.m. The VP of Finance is going to also be allowed into email, company intranet, and files and folders from the laptop. However, if the VP of Finance tries to use a privately owned tablet on an external network to access that same information, additional restrictions apply. So for example, with a tablet, the VP of Finance cannot access the financial application. Email and company intranet are fine, and files and folders are restricted to 6 a.m. through 8 p.m. completely, which is an addition to the file and folder restrictions from the laptop. So we go down to AP clerk, which is a different role. We see that the AP clerk has additional restrictions on what he or she can access because of the role they are in within the organization. So I want you to take a moment and think through this, because this is not that complicated. This is just a matter of determining who is accessing, what they're using, who owns that device, where they are, what they're trying to access, and how we're allowing them to authenticate. And based on those conditions, we compare those to policies that we've set up in the system, which, if we look at a Cisco application, it looks like this. And we either allow or reject their request for access. So in this particular graphic, you can see that we have policy teams that create policy. Those policies obviously are going to be set up based on business requirements as well as regulatory constraints and risk. Anytime that a device wants to connect, whether it's internal or external, it has to go through the policy check to determine what it can access and what it can't access based on those conditions that we looked at in the last slide. And that includes all applications, and that should also include vendors. A vendor is a role. So what can a vendor access with a laptop sitting in a conference room in your organization? So this is an emerging approach to access control. Without this, it's extremely difficult to manage bring your own device security. Now we're going to take a look at trust. First, basic trust is a level of confidence that a system will operate as expected given its intended operational environment. So for example, if I build a system to function securely in the data center, then any checks, audits, any kind of monitoring, that if that system works in the data center as I've designed it, then the level of trust is reasonably high. But if I take that same server and put it out on the manufacturing floor and it's not behind closed doors, how does the trust change? It wasn't designed for that environment. It was designed to operate with a level of confidentiality and integrity and availability within the data center. By taking it out of that physically secure area and putting it out on the plant floor, they've now changed the level of trust in that device. It's dropped significantly. Distributed trust is ensuring trust regardless of where a system or device is used or with what it connects. This includes organization network connectivity trust and trust in the cloud. So I have to extend trust. I start with this. So every system, every device that I put onto the network should start with its own internal level of trust. Trust is built by controlling everything that happens as the system boots up, how the different applications and services within the device authenticate to each other and to external processes and devices. It's really attack surface management. So if I take and ratchet down the attack surface on this e-commerce server, for example, to a point that is high trust while still allowing operational efficiency, then I've hit my trust objective. When I place it into the network, it also inherits the trust of the network. The network itself, or the segment onto which I put that device, is a trust context. So, for example, if I put this e-commerce server into a network segment that processes restricted data, and the trust of that segment is very high because of the controls and monitoring I have for that segment, then that e-commerce server is going to inherit that network segment trust, that high network segment trust. On the other hand, if I take a server that has high trust and put it into a network segment with low trust, what does that do to the overall trust for that server? You took a high trust device, put it into a low trust network segment, and now you just raised the risk that that server will become a target. Again, we're looking at device attack surface. So remember I talked about in the last slide that trust begins when the system is starting up. That's what this slide is showing. This is a traditional BIOS startup. You notice that we have the hardware, we have firmware that is loaded from the BIOS chip and from other devices. We have drivers that are provided by the operating system vendor as well as the device vendors. And on top of that, we put the operating system and the business applications. The area of potential problems that destroy our foundation of trust on boot up are the drivers and firmware. In a traditional boot up environment, we have very few ways to check to determine whether the drivers and the firmware and any hardware that is found is supposed to be there. So how do we determine whether or not somebody added something to the system they shouldn't have added, or that they have put in a driver either remotely or locally that is not the same as the driver that was in there 2 days ago? We should be able to know that. And with the new approach to startup for systems, both desktop, both desktop and for servers, we can now do that. And how we do that is with the Universal Extensible Firmware Interface, or UEFI, UEFI. And what happens is the old traditional BIOS is eliminated, and the UEFI takes control of the boot up. It will check to determine whether or not anything has changed since the last authorized boot up, and if it has, it will react according to policies that are set up by administrators. It also checks to make sure that all firmware, that all drivers, and all operating system components are properly signed and therefore are safe. Now, once the boot up is complete, we can pretty much trust this device at least down below the application level. So now all we have to do is worry about what's going on with applications as they're operating. So this helps a lot with rootkits, because the early launch anti-malware checking, the ELAM, which you can see in step 2, is going to check to make sure that there's no malicious driver loading that we don't want on that device. So this is a big change, and it's a good change, because getting rid of rootkits is very difficult. This will help with that. If you'd like to learn more about UEFI, check out the book chapter at the link shown on the screen. This slide is part of an attack surface assessment. And remember, I talked about trust also includes how you control what processes in a system, how they communicate with each other, how they authenticate with each other, and that's what this slide represents. So each object, could be a process or a data resource, has a set of access rights. It uses those rights to reach out over channels and protocols to connect to other resources. Or a subject will also reach out to that device or process and try to connect. Based on the set of access rights, two things will happen. One, the object will either be able to communicate with other objects or be blocked based on security that's been configured by administrators and developers. Or it will be allowed to connect. So you have drop connections and you have accepted connections based on access rights. This kind of approach helps to ensure that processes only get to talk to processes that they're allowed to talk to. So if an attacker took control of a system and tried to access another system over a channel that was not allowed by access rights for the owned object, it will fail. So what we've done is we've eliminated one attack vector for the attacker. We've limited what the attacker can get to based on process access rights. Next, we're going to talk about trust boundaries. A trust boundary is a point at which data moves from an area of one level of trust to an area of a different level of trust. So if we look at these two network segments, we see that they're both secure VLANs. But let's say that the one on the left is only handles confidential data, and the one on the right only handles secure or handles restricted data. Also, you see a data center trust boundary. That data center trust boundary represents everything that's on the outside of the data center trying to access information inside the data center. For the most part, unless it's other systems, other networks within the organization, or other or vendor partner networks, for the most part, everything on the other side of that data center trust boundary has a lower level of trust than what's in the data center. Any data that moves from the secure VLAN on the left to the secure VLAN on the right must be controlled in a way that ensures that the trust is the same in the target network segment as it was in the source or the home network segment. In this case, since we're confidential on the left and restricted on the right, that's not a problem as data moves from left to right. However, when we go from right to left, we have a different problem. If we take data out of the network on the right and move it to the network on the left, we have to make sure that we only move data that's classified as confidential. We cannot move restricted data from the VLAN on the right to the VLAN on the left because the VLAN on the left is not considered at a high enough trust level for restricted data. So that managing trust boundaries is very important. Now, these are two examples of internal trust boundaries. Other trust boundaries exist, like this. So I have my data center trust boundary, and now I have a cloud service provider. We know for a fact that the internet is not a trusted network. We also, when we first sit down with a cloud service provider, we're assuming that there's no level of trust, that there's an insufficient level of trust between the network segment that will be communicating with the cloud service provider and the cloud service provider's network. Through assessments, through discussions, through review of documentation, once we approve of the cloud service provider's network segment that is communicating with our network segment, then it can look like this, where we extend the trust from our network out to the cloud service provider. Now, we obviously are not going to trust the internet, so we'd use something like VPN or a point-to-point connection so that the internet is completely removed from accessing the data. But at this point, we know that the level of trust at the cloud service provider is the same as the level of trust in our network. Does it mean it will stay that way? Absolutely not. Everything changes. So we have to make sure that in our contracts with cloud service providers, we maintain the right to conduct audits on the service provider's network, at least those sections that affect our data. So this means it doesn't matter whether there's applications hosted there, whether we back up to the cloud, doesn't matter. As long as our data is up there, or as long as our data passes through the cloud service, and we must maintain a specific level of trust so that we can ensure that our data is secure, we have a right and a responsibility to make sure that the cloud service provider is doing everything it can to produce security outcomes that we expect. Now, once we've done all of this, and we've put in our controls, and we've written our policies, and we get audited, and everybody's happy, there's still risk. We can't eliminate all risk. We talked about this before. So what we end up with after we apply all of these controls is aggregate risk. The level of aggregate risk that exists after controls are applied must comply with management's appetite for risk. So in other words, management has to decide whether or not the aggregate risk is too high. If it is, then we have to go back and we have to make adjustments on our controls and processes. So here you see that the probable threats on the bottom passing through our devices, which have their attack surfaces locked down to a reasonable appropriate level. Those two levels form probability of occurrence. The probability that a threat can leverage a vulnerability within one of those devices, or, as we can see, the user, as in social engineering. Above that, we have value of the data or its sensitivity. If the data is high value, as we saw in our risk formulas, we know that the risk is going to be higher than if the data has low value or sensitivity. So once, let's say that the weak passwords allow access into a server that has all of our customer financial information on it, that would be a potential high business impact. However, notice that above value and sensitivity we have response posture. How well we are able to respond to an event. And that also includes how well we're able to detect an event as close to its initiation as possible and to contain and eradicate it will impact how much damage is done to the business. You put all of those things together, it's like going through filters. You have your probable threats, which go through the filter of your attack surface management, which go through the filter of how sensitive the data is that's affected, up through the filter of response, and out the other side comes aggregate risk. The risk that's left over after you've put in all of the controls that we've talked about in this lecture. So how do we know whether we're doing the right things? How do we know what the starting points are for making sure that we've got all the gaps closed? Well, we use standards of best practice. There are four places that I go when I want to start something new, or if I want to do a double check on something that I'm working on. The first one is COBIT, Control Objectives for Information and Technology. And this one is from ISACA, and it is what the auditors are going to use when they come in to do a SOX audit. It's just the one they picked. In the COBIT V version 4 was pretty far removed from what's in the next line, the ISO 27002 standard, which is comprehensive. COBIT was more concerned only with financial, but COBIT V5 has expanded what it covers to include almost everything. So if you only want to apply one standard, because you have to apply COBIT if you're publicly traded, if you only want to apply one standard of best practice, COBIT's probably your best choice. The ISO 27002 is closely aligned with the HIPAA. It's a code of best practice. It's an international code of best practice that began in Britain and eventually expanded to be an international standard. It is what I used for years until COBIT v5 came out, and it is a comprehensive standard of best practice that provides a good starting point. Remember, these aren't standards as we understand standards that support policies. These are not things you have to do. These are simply recommended approaches to securing certain domains within your enterprise network. And by domain, I mean business continuity, network security, communication security, those types of things. IDLE is another way to approach security, and it also includes things like change management. IDLE provides a lot of detailed information about how to build different practices within your organization. So like I mentioned, change management. It'll have the change management directives, or not directives, but the change management recommendations in ITIL are very detailed, step by step, on how to build change management process, how to populate your change advisory board, and how to design your change process. So it's very valuable when you're trying to put together something something complex, some complex approach or some complex program that is targeting a broad spectrum of things, like, for example, change management. NIST, the National Institute of Standards and Technology, is where I go most often, and this NIST has a whole collection of documents. Each document addresses a specific area of security. And although these were written for use by government agencies, they're very applicable to what we do every day in private industry. And when you're sitting down to try to design controls that you've never designed before, or that you haven't designed in a while, go find the appropriate NIST document, read it. Doesn't mean you have to do everything that's in there. Remember, these are all starting points. These are a foundation, a place from which to build. And every business is unique. Every business has its own operational requirements. So you're going to make changes from these foundations. However, what these do is prevent you from missing things inadvertently, and possibly give you some additional perspectives into areas that you haven't looked at yet, or that you looked at in a way that did not provide all the information about risk that you needed to protect your organization. And that's it for this week. Be sure to read all your assigned reading, and any questions you have, please ask them in the main forum in the post provided for that purpose. Have a good one.